So, hello everybody. I'm Julian. This is Zhechko. We're from Technical University of Munich, obviously. And I know that we're blocking your way to dinner, but still we would like to present a couple of new attacks against dynamic binary instrumentation to you. So I would like to start with a brief survey. Who of you actually knows the term dynamic binary instrumentation? Please raise your hands. So that's about a third, at least a quarter. Okay, so of those of you who actually know what dynamic binary instrumentation is, who of you actually uses this technique to analyze binaries of unknown sources? Still a couple of hands. Okay, and who thinks this is actually a good idea? I see one hand, I see two hands, three hands, I see. Okay, so we will discuss this in this talk. Just to bring us on the same level, dynamic binary instrumentation is a tool that you can use to inject or add new functionality to already existing binaries. You don't need to have the source code for this, that's quite cool, and it's mostly done in two fashions. It's either done statically, so where you have an existing binary on disk and you rewrite it there by just adding new instructions, adding new code, or even let it do your compiler, and then execute it. The other way is dynamic binary instrumentation, which is what this talk is about, where the instrumentation code is just added lazily once the interesting instrumentation points are reached. So that's dynamic binary instrumentation, that's what we're going to focus on. There are multiple frameworks you can use to do dynamic binary instrumentation, for instance, IntelPin, Valgrind, DynamRio, DynInst, and QBDI. And to our perception, IntelPin is the most useful one, or the most used one at least. Sorry, not useful, but the most used one. So that's why we're focusing on IntelPin in this talk. And in order to actually understand how DBI works internally, we actually have to see that there are three main components. The first component is the actual target application. So that's the instrumented application you want to change, you want to add functionality to, that's your binary you want to change. The second component in the address space is the pin VM, which is actually based on a dynamic JIT translator, or we call it compiler here, that does the translation from the instrumented application as it is in memory into a code cache. And then the third component is a pin tool. I will also refer to this as an analysis tool, which is basically a plugin that the analyst can write in order to actually control the execution of the pin framework. So, and how does this play together? Well, let's assume that we actually want to instrument this application here, and we want to get notified when this branch here, so the branch from the first basic block to the second basic block at the bottom left, gets executed. So if we did that, then what would happen is that the pin VM would fetch the first two basic blocks into memory, and the JIT compiler would actually start translating them and look whether there is a callback that the analysis tool requested. So for instance, the analyst might have requested, hey, whenever you do a conditional branch, conditional direct branch, then give me a callback. So that's what would be written in the pin tool, and that's what the pin VM checks for. And then let's say there is one such callback, then the code gets JITted, and the actual new code is getting inserted here, right? So these are the original basic blocks, and here we have a new one which contains the additional code. Kind of simple. And then once the JITting is done, pin actually switches from JIT mode to executing what is there in the code cache. And once it's done with that, so it places the instruction pointer there, the execution continues here, and once it's done, it switches back to the VM context. There are two very important observations at this point. So number one being, as you could see, the original code here is never executed. It's just getting copied into the code cache and executed from there. And the second observation is that the code cache is exactly this. It is a cache. So whenever you encounter a basic block twice, then there is no re-instrumentation being done. So it's just instrumented once and then placed in the code cache, and if it's already there, then it remains there. That's important for later. And as you could imagine, DBI is quite powerful, so a lot of people use it. So the basic usage is, for instance, to do some taint analysis, which is basically just data flow analysis in binaries. Some of you might know Valgrind's leak detector, which basically you can use to find memory leaks in your application. But there are also more interesting applications focused on security, which is, for instance, what I call program shepherding, which is the case when you have some legacy code lying around without access to the source code, and you know you have to put that on your public internet because it's, I don't know, a fancy web server, but you don't trust the programmers and you suspect them to have made mistakes, and therefore you write additional security checks that you want to inject into that binary. So that's what's called program shepherding. The CFI community uses it a lot to deal with what they call common off-the-shelf programs. And then there's, of course, a more obvious use case to use Intel Pin for malware analysis. And there are a couple of tools used for this. For instance, we had last year at Recon the Maze Walker talk where they proposed exactly this. Also, there is this Lighthouse IDA plugin that some of you might know to actually measure code coverage in unknown binaries. Alexei used this today morning. And even IDA ships with a Intel Pin-based debug server. So what I want to say is DBI is really everywhere. And this inspired us to actually take a step backwards and to think about, okay, hey, what security properties do we actually need from any dynamic analysis system that is capable or should be capable of dealing with malicious code? And it turns out there is actually a research paper from 2003, and there the authors actually propose 3 properties that are needed. Number 1 is interposition. So this means whatever your analyzed program is doing, you need a synchronous callback to your analysis tool to be notified when something interesting is going on. It's kind of obvious, I think. Then you need inspection. So whenever you reach those instrumentation points, you actually need to have full access to the address space of the inspected program. So you want to examine all memory addresses, you want to see the register contents, and you want to freely modify them. Then a third one is that obviously you also don't want the analyzed tool to actually tamper with your analysis tool, because that might, well, ruin all your results. And a fourth one, which was added later, is actually stealthiness. So whenever you're executing something in a debugger, for instance, then you might know that infamous is debugger present check, and then evasive malware might do whatever it wants, but not what you intended it to do. The same problem exists for DBI. So once something is able to determine that it's being run in Intel Pin, you're running into trouble. And these 4 properties here, we will question in this talk, and we will start with stealthiness and deconstruct stealthiness, and from there start attacking isolation. And once we are done with isolation, well, obviously it's GG, and interposition and inspection are also gone. So that's our agenda for today. And with this, I give it to Zhechko.
Okay, cool. So now I will show you how we can break the stealthiness of the instrumentation framework. As you could have guessed by now, the instrumentation introduces a lot of noise in binaries instrumentation, and the instrumented program can actually search for these subtle differences to get if it's instrumented or not. This is nothing new. Falcon and Riva already did that at Recon 2012, and we extended their research with other techniques to detect that. In Linux, their research was only based on Windows, 32-bit, and we divided our detection techniques in 3 categories: environment artifacts, JIT compiler, overhead, and code cache artifacts. We developed a tool which is open source, and tested it in Pin and other common DBI frameworks. You can see some simple output of it here. Okay, let's start with the boring stuff. The instrumented application can search its mapped pages. And you can see here, it can list all map pages and their permissions. You can see here that's a normal application, nothing unusual. And when we instrument the same application and look at its mapped memory regions, you can see that, first of all, there are a lot of them, I mean, more. And you can see that in red, there are pages which are mapped as simultaneously read, write, and execute, which is pretty bad and very uncommon for a normal application. And what an application can do is just search and count the number of pages which are RWX, and if there are a lot of them, it means that it is instrumented. Next. The instrumented application can query some environment variables. Okay, in normal program execution, there is nothing interesting there. But if we instrument the same program and list the environment variables, we can see some very interesting stuff. For example, there are a lot of them, I mean more. And for example, you can see at the bottom pin injector 64 LD library path. Yeah, it says pretty clear that something's dodgy is going on here. Okay, next. As Julian already said, there are this switch between the virtual machine and the pin and the execution of the code is done by saving code registers in the memory and then restoring them from other memory, and which is a common pattern, which we can just search for that. And finally, there are some timing things that we can search for timing attacks. Timing things that we can. Sorry.
Side channels.
Side channels. Thank you. That we can that the application can observe, which are introduced by the JIT compiler. Now that was the boring stuff. Sorry. So to the more interesting stuff. When the normal application expects that its instruction pointer will be in the text section. However, as Julian already said, the original code is never executed. It is JITted and instrumented and saved in the code cache and executed there. However, what pin does is it masks the instruction pointer, and when the application asks for it, it will give a pointer, an instruction pointer which is in the text segment. But how many ways do you know to get the actual instruction pointer? Yeah, a lot of them. And actually, interpin does not mask all of them. For example, if we execute a floating point unit instruction and save the context with fxsave, it contains the address of the last executed FPU instruction. And an application can, an instrumented application can execute fxsave, gets the instruction pointer, and get it with some other way, some return pointer, for example, which will be masked by pin, and compare these two values. When they're not the same, it is instrumented. Okay, now we know that we have a JIT compiler, and the instructions are compiled, and it can happen that some instructions are emulated wrongly, and this happens with the most normal instruction, a syscall. As you surely know, it is a way of the application to communicate with the underlying operating system. Here, you can see a normal application which prints to the console hello, Recon. And when we execute it, we move the parameters to their right registers. In AX, we set 1, which means right in x86 64. And when we execute the syscall, what happens is the message gets printed to the console, and we get our return value, the number of printed characters in array X. But what most people forget is that in RCX lies the current RIP value, which the kernel needs in order to restore the normal program execution after the syscall. In the case of pin, what happens is that this syscall is executed somewhere deep in the instrumentation framework, and the only thing that reaches back the application is the return value. So in R6, we don't have the saved RIP value. What the application can do, search, check if the R6 is equal to the saved RIP. If not, it's instrumented. Now for the next one, I would like to show you something. Okay, this is a normal program, not normal. It tries to execute code, shell code, which is residing on the stack. Normally, this stack is marked as non-executable. So we have a shell code residing on the stack, which is not executable, and we try to execute it. Of course, when we do that, it crashes. Okay, nothing unusual. Now, let's make a survey. If I instrument that same program, what will happen? Will the application crash again? What do you think?
Yes, no question.
What do you think? Will it crash? Just raise a hand if you think. Cool, yeah, that's actually very correct. Sorry?
So the stack is not executable at this
The stack is not executable.
Okay, in the memory mappings. Yeah, okay, but if you look closely, then you would see that the stack is actually not executable so far.
Yeah, okay. So the stack is not executable. The program should crash now, but what happens is it actually continues its execution and spawns a shell. That's actually pretty bad. What happens here is that pin does not just continues executing whatever instruction you give it. As long as it is readable, it will execute it. Yeah, which is actually pretty bad, because that gets us to 1990s, when I was not even born, and now, I mean, every instrumented application can execute data, effectively breaking NX, DIP, whatever you tell it. You can execute normal data in 2018. As long as you're running it in Intel Pin. Okay, now we broke stealthiness. By the way, it is here because it is a very nice detection technique. If we can execute non-executable memory, it is instrumented. Yeah. Okay. Cool. Now we broke stealthiness. Can we make it worse? And actually, we can break isolation, and which is pretty easy with the given tools which instrumentation gives us. I mean, we have read, write, execute pages. We have application and DBI framework residing in the same memory. What more do we want? We chose two attacker models. In the first model, the attacker, me, develops a malware and gives it to you to analyze it, and you instrument it. The second attacker model is I host a server which is instrumented, and you have access to that server. And you communicate with it. Okay, let's see now the first attack. Now I will show you how you can break out of the sandbox, of Intel-Pin sandbox, with only 7 instructions. First of all, we use one of our detection techniques. It is the getting the real IP instruction pointer. How we do that? This code is executed once, so it lands in the code cache. We execute one FPU instruction. In this case, it is FLDS, which just pushes a 0 to the FPU stack. Then we save the context with fx save, which at array x, that location. And from there, we get the location from that context. Remember, it contains the address, the real address in the code cache of this instruction. And on that place, we inject some code. In this case, we want to jump to some other code which we control in the same application. Now, in the end, we jump again. We execute the same thing again. As Julian already said, the JIT compiler will see that this code sequence is already JITted, instrumented in the code cache, and will execute it. It will not check if this code sequence has ever been changed. It will just execute it, and that's what it does, effectively executing our injected code and jumping outside of the sandbox. Effectively, what happens now is that Intel-Pin still thinks that instrumented code is executed, and awaits that at some point it will return back for another JITting and instrumentation sequence. But that never happens. It just continues its execution, and that's it. Now we have a demo here. So, okay. First, this is a pin tool which tracks the execution of all Cisco instructions by the application, and it prints some information about them, such as input parameters, what was the Cisco, and so on. Here, you can see these prints which start with application. These prints are made by the application, by the instrumented application, and you can see, if I actually can, okay. You can see here. I can move that. Cool. Thank you, Apple. You can see here that the application executes it says that it executes a Cisco get PID, and the pin tool records it, which is completely normal. Now, when we enable that technique which I showed you on the previous slide, and execute the application again, I show that Ciscos are registered. We can observe that the application executes again the same syspid, get PID, but there is nothing from the pin tool. It just continues the execution, exits, and there is no interposition here. There is no feedback from the pin tool. Effectively, what we have done here is we broke isolation, we broke stealthiness, and in this way, we broke interposition and inspection. And again, just to note that because IntelPin does not, this is only possible because IntelPin does not track if somebody has modified the code cache. Cool. Now for the last part of the presentation, I will hand over to Julian.
Okay, thanks. So Zhechko showed you what you could do as a malicious malware author to actually escape any analysis. And I actually asked myself, so assuming we have a program, a legacy program that contains a bug, how does exploitability, or how easy is it to exploit that existing bug depending on whether that application is running in IntelPin or without IntelPin? And the example we're going to talk about here is CVE 2017-130809. It was a bug in wget in versions prior to 1.19.2. And in this case, actually, it's the server exploiting the client. So, but nevertheless, we're either once instrumenting the client and once we're not instrumenting it. And the bug itself is triggered by using chunked encoding in HTTP redirects. I didn't know that this was actually possible. I'm not a web guy, sorry. And if you then there specify negative lengths, then you get a stack-based buffer overflow. So you can overwrite a buffer of fixed length on the stack, and then, as usual, overwrite the return address that is directly stored behind it. However, I guess now the resolution of the protector is about to fool me. Yes, okay. I'm still trying to walk you through this one. So how exploitation might change or changes in case of the presence of pin. So this is the malicious HTTP response from the server that I just showed you. And this here is actually the state of the CPU at the time it tries to return from the function that has the overflow bug. And what we already note here is that, I know you can't read that, but here is RSI actually pointing to what I named shellcode because it's part of what the server sent to the client. So we already have a pointer in RSI that points to something we control. That's good. And the problem we have still, though, is ASLR. So we don't know where this buffer actually is. So I know there's this address 7FFF whatever, but if you run it outside of GDB, then this address will change. Also, wget is compiled as position-independent executable, so we actually have zero idea of where we should jump to. And now my question to the audience is, what would you do in such a case? So you control a saved return value in the stack, but you have no ASLR leak. What do you do? Nopslet. But then still, okay, so you propose to actually increase the payload and hope that you will hit the payload then, right? Okay, but ASL ultra entropy is 32 bits nowadays, so that's complicated. So what else can we do? I see, nobody wants to win that beer. The image-based granularity, I can tell you by mind, out of the top of my head, but it goes in that direction. The granularity of ASLR is page-wise. So ASLR on Linux operates on page granularity, well, like virtually on every other system, and therefore the lowest 3 nibbles of any pointer are constant. And we can abuse this to actually do what we call a partial pointer override. So we can just start not overwriting the full pointer stored on the stack, but just the lowest most byte and the second lowest most byte. And if we do that, we actually trade in the space of ROP gadgets we can reach versus stability, right? Because as I told you, you can't read that, so that's actually 4 nibbles here. 3 of them are constant, so we have to brute force 1 nibble. And by this, we actually gain access to at least those ROP gadgets that are close to the original return locations of the vulnerable function. That's exactly what we're doing. And what you find there is, fortunately, a so-called stack lifting gadget, which I depicted here, which does nothing else but actually shift the stack pointer from its current location to some other location. And why do we need that? Well, the nice part is that there is actually a pointer on the stack here that points to something, which you also cannot read, which came from the malicious server again, and which basically is the UTF-8 encoded version of the cookie. So if we manage to actually move the stack pointer here and then return, like what this gadget does for us, then we jump into what we actually specified in the cookie. And as you can see, normally the program would just crash because it would say, hey, this is data, you're trying to execute data, I'm not going to do that. So the operating system kernel would just kill you. But as we learned earlier, when we're running an Intel pin, we can execute everything. So we just jump into that UTF-8 encoded cookie, which, by the way, just happens to be a push RSI followed by a C3, which happens to be a ret. And push RSI, ret, is effectively jump RSI. And as we remember from the beginning, RSI actually points to what we specified in our response. So there we get actually code execution. So I would like to demo this. Let's see whether I can actually deal with, I think it's that one. Okay, let's see. Okay, so at the top we have the malicious server, which is just listening on localhost. And at the bottom, as you can see, we're doing some shell foo, because as I told you, our exploit probability is just 1 to 16, because we have to brute force one nibble. And what we do is we take Intel pin and let wget connect to our malicious server and, well, try to see what happens. And once we're done with fiddling with the input, then you can see, okay, so the while loop starts, and after a couple of connections, what we actually get is, if you look at the top here, magically now the server has a shell on the client. Or, yay. And that's all due to the help of Intel pin, thank you. Okay, let's wrap it up. If you remember nothing, remember this. If you are actually using Intel pin to inspect binaries of uncertain origin, then please be aware that this binary is capable of determining whether it's being instrumented or not. So it might behave in completely different, unintentional ways. And it's also possible to evade your analysis, because as we showed earlier, you can just jump out of that pin VM, you will not get any instrumentation point callbacks anymore. And then the last point, as you saw with wget, if you think you should take your legacy code and then add security checks by means of writing a pin tool and implementing, for instance, a shadow stack to check return addresses, then you might be doing more harm than good because, well, of all those flaws that we can find when we're dealing with Intel pin. So please, please, please be careful when you use DBI frameworks in context of security. Think about letting them run in a virtual machine or something that actually provides proper isolation and not something that, well, has analysis engine and the analyzed binary within one address space. Okay, as usual, we upload all of our sources, all of our proof of concepts, such that you can, well, reproduce our results and play with them. Also, what we presented here is basically just Zhechko's master's thesis, which I used to supervise, so I'm just leeching here. So you can download that as well. Possibly he's currently looking for a job as he now finished university. Also, there's the slide deck online. You can find the link there as well. We told Intel about our findings, but I guess they're busy with other things nowadays. So we're still waiting for an answer. They didn't have too much time that I have to defend them. And as we just learned today morning, there's also going to be a research paper on the topic, which is going to appear at ESORIX 2018. Thanks for your attention. Are there any questions?
Okay, first question. First beer, or how should we handle it?
Best question gets the best beer, or gets to choose first.
Okay.
The exploit that you demoed in the last demo, did you change that so that that exploit worked on both a instrumented and uninstrumented execution, or was it just targeting an instrumented execution?
So there was no exploit going on against an uninstrumented version. So that was just the version running in Intel pin you saw, but I did not tailor it to any needs. So I just downloaded the source code and compiled it, and that's the binary we attacked.
But my question was more for if you're doing the attack, you wouldn't know if you're going against an instrumented or uninstrumented version.
You wouldn't, of
course. So has there been any research into like having one exploit to rule them all?
Yes, but that I think goes more in the direction of I write a malware and then this malware is capable of determining whether it's running in pin.
Hello. I have a question, please. So is this? It seems like an incredible.
Where are you? Sorry, I can't see you.
To your left. Hey.
Oh, back there.
So this seems like an incredible oversight by Intel. Is there any way that they can create a mapping of what sections are executable or not? What exactly is happening? Are they aware of this, that you can just execute shellcode on the stack of a application that should not have that happen regularly?
I guess they just missed that one check to actually check whether a region of code is executable prior to chitting it. So I guess the fix is one line on their side.
And they know about it now.
Hopefully.
And hopefully they will fix it.
I was just curious if there was a valid reason for ignoring the execute bit. Like,
I
if
can't
there was a
imagine one,
performance
but
reason or
I don't think so. I mean, why would you do that?
that was my question. Like, was there a specific reason or use case?
No, I mean,
I guess there's just no check going on, and they just fetch the data into the JIT compiler, and the jitter, of course, returns executable code. So,
yeah, generally we think that, I mean, we strongly think that this should be checked.
One more beer left.
one will be left.
Do you have any idea how common web-facing instrumented applications are?
So, according to academia, very common. So far, I haven't seen any.
Sorry, say the last word. So
So,
far.
I'm not aware of any situation where you would do that, but what I'm saying is that there are lots of publications where people suggest you should do that.
Ah, okay, thank you.
About just here on your left. So about that wget case, I was wondering, so Pi was enabled, but there was no stack cookie?
There was no stack canary, yeah. As I said, I did not fiddle around with the makefile. It's just what the compiler spit out. Where are you? Again, I can't. Sorry, there. Always hiding behind the speakers.
It's coming off the shelf.
Okay.
Took it.
Hi guys. Okay, my turn. So nice talk. So I have a question. So my question is about if you try to investigate if this problem is pin only or generic for any other dynamic binary instrumentation framework.
Yes, we try that in PIN, in DynamoRio, and in DIN, and in QBDI. I mean the frameworks which we presented in the start, and they all have that. They all execute code, which they all execute data, code which is residing on non-executable.
Okay, so here you show only for PIN, but it is generic. Okay. Thanks.
Okay, I do not see any more questions. Then thank the speakers
Right.
again, and fight for a beer.